Well, welcome back to our course on system engineering. In this lecture, we're going to be talking about the future of systems engineering. And this is going to be the last chapter, the last lecture related to the material that we're covering in our textbook. So I think it'll be interesting to be thinking about the future. Those that are taking the class are likely already thinking about their future. So let's start out with an introduction and motivation. So this chapter and lecture concludes with a look forward to the future of system engineering, how it has evolved, and where future system engineers would look to ensure the profession remains a timely and relevant contribution to society. We have seen how system engineering has matured from the aerospace and defense communities to many different domains, such as transportation, cybersecurity, healthcare, as well as incorporating different aspects such as human factors and software engineering. We look towards the future of system engineering to identify changes and disruptions and seek to draw inspiration on why and how a system engineer needs to continually adapt and grow in order to remain relevant. So 4 changes are identified to help motivate these changes: change in the user needs, system mission changes, competition and teaming changes, as well as the changing threat. These disruptions may also cause the system engineers to adapt to the environment and workplace, that is disruption in technology, processes, and people system interfaces. The successful system engineer will look at disruptions and opportunities. Each of these areas is intended to identify where the system engineer's role can help to contribute to the challenges and advance the practice. And so what we're going to do is we'll talk about these in more detail one at a time. So for the user needs change, some of the changes may be within the user needs themselves. As the user becomes more astute in learning the system engineering capabilities and operating their legacy system in today's environment, they may also look towards the future in determining their future spirals and versions of their systems in order to stay ahead of the competition, threats, and environments. Other current events, such as climate change or conflicts, may necessitate a rapid change of capability that is needed by the system, or introduction of a new user community and expertise that needs a change in the existing system. The systems engineer would then need to elicit revised user needs and help to translate these new needs into system and functional requirements in order to develop the new capability. For system mission change, sometimes current events may cause changes to the system in ways that it was not envisioned to originally operate. As systems are inserted into the operational environment, these systems may not have been developed with the environment in mind, but the operator must accomplish their mission with the capabilities they were given. Sometimes they will adapt the system in ways that the original designers and testers had not imagined, which provides valuable lessons learned and insight into the next version of the system, particularly if it was successful in the field. Other times, the operators may discard the current system if it is not suited to their purpose. These system missions may mature over time and take on additional missions to remain relevant in the field. Military systems that are given additional missions over time include air defense destroyers and cruisers will modify their original missions to take on land attack and ballistic missile defense roles to keep up with the emerging threats. Similarly, air-to-air fighters will evolve to also take on air-to-ground mission to remain a relevant contributor on the battlefield. The system engineer would then have to evaluate how the existing system can still perform its original mission, as well as consider the new requirements, architecture, interfaces, and testing that would occur while affecting the new capabilities into the new system. For competition and team change, as the various systems evolve in their business operations, often their competitions will also change. Sometimes these will be in the form of changing system development strategies in order to increase market share, or change the company's direction in an attempt to capture business in a new area. These changes may introduce additional systems and capabilities that the stakeholders may be interested in, forcing their competitors to consider adding these capabilities or creating new capabilities in response. These changes may also be in response to changes in the user and or mission. The system engineer may need to elicit additional requirements, evaluate existing requirements, or consider modifications of the user needs and ultimate architecture while considering how these changes would affect the current system configuration. Teaming relationships may also emerge as a result in the change of an environment, and former competitors may now become partners in certain proposals. Systems may need to change their interfaces and interpretation of data in order to interoperate with these new partners to enable the desired end result. System engineers should be well versed in describing these interfaces and enabling the knowledge transfer if the situation occurs. In terms of threat changes, finally, the threat may change their behavior as well in response to the system's development and promise of future system performance. Through evaluation of the threat performance, the system engineer should be able to help analyze the current system, identify the gaps based on the desired outcomes, and help to derive new requirements and capabilities to address these future threats. The system engineer will need to be more agile in this approach, as sometimes the intelligence picture of the threat is often vague and incomplete, so analysis without the full data may be needed. The timeframes in which to effect these changes may also need to be accelerated in order to stay ahead of the threat capability, and different design options or trade space may be considered. Then we have a couple of disruptions. First of all, the technology disruption. Insertion of new technologies into society can quicken the pace of change required for users and industry to adapt to remaining relevant. Increasing populations are much more readily accepting of new technologies. The common technology disruptor examples are the Global Positioning System, GPS, to provide precision location services, and the internet to provide global connectivity. Other disruptions are in the area of energy sources, miniaturization, network evolution, and new materials introduction. System engineers can help to envision the ways that new emerging technologies can augment existing new user needs as well as elicit new needs. System engineering can also help to modify existing system architectures to accommodate these new technologies and develop upgraded architectures as the new technology becomes more widespread. There's also the disruption of processes as government, companies, and users find different and innovative ways of performing their objectives. Eventually, a shift of policies, procedures, and standards may need to be developed in order to help codify these processes. Before these procedures can be formalized, the system engineer may need to help find common definitions of these processes and assist users with the transition to the newer processes. The systems engineer can help to conduct some of the user needs, cost, and benefit analyses to show a legitimate case to switch processes. Other ways for system engineering to be involved is to test these procedures, these processes to ensure that they are valid and can provide additional value. Finally, for people and system interface disruptions, interactions between users and systems continue to evolve as newer systems are introduced into society. Common example is the iPhone with the unique at the time, user interface, and how it has affected a large portion of society to interact with the digital world. Other examples are the ride-sharing program to disrupt traditional taxi services as new combination of how users and systems interact, and as newer services emerge, the system engineer can analyze how the impact to the user will change and help shape the newer requirements for different users. As this may also affect society at a larger scale than a single system, the systems engineer may be called upon to perform holistic analysis on the greater society as newer systems are introduced. Okay, we also have want to consider what are the areas to apply the system engineering approach. The number is growing, and so here are a handful. Future systems engineering efforts may be applied to different domains other than the traditional defense and aerospace projects. For some domains, a simple application of the system engineering lifecycle model may be applied, while other domains may require a more holistic approach to adequately develop the system concepts. Even within traditional domains, the introduction of autonomous capabilities, intelligent networks, or global interfaces will require special attention. So listed here are selected domains, but it's not exhaustive, that could either benefit from system engineering thinking and approaches or require techniques beyond the traditional system engineering approach. First, we have healthcare, and I might also include the exploration of biological systems as a corollary of this. Healthcare combines a variety of stakeholder systems and domains in order to adequately capture the entire ecosystem that patients, physicians, nurses, and engineers need to contend with. New approaches with human systems interactions are providing healthcare services, some of which may be embedded within the patient in order to provide the data. New approaches may be needed for the system engineer to incorporate additional policies and standards when it comes to considering safety practices and requirements. Testing practices when it involves embedded systems may need to consider a different approach. The healthcare domain also has a complex and interdependent ecosystem to include factors such as technology, insurance, government policies, hospitals, human factors, social factors, and home health care. Each factor has an influence on one or more factors that when treating the patient, so a holistic system engineering perspective may be considered while developing the solution sets to address the stakeholders' needs. Note that these interdependencies may differ when operating in different parts of the world, so the system engineer may consider a tailored approach to systems development when serving the intended population. Global interactions and threats provide challenges and opportunities to apply systems engineering practices to use technologies and services not previously considered. For transportation will likely rely on both greenfield and brownfield system engineering approaches. A greenfield system engineering approach can help identify unique transportation needs that require new infrastructure and new systems to provide the capability. A brownfield system engineering approach can help leverage existing infrastructure and provide an improved capability to integrate with the existing systems. In both cases, system engineering can help address transportation needs, ranging from the most congested urban cities to the most remote rural areas. In addition, as transportation modes change, the systems engineer will need to not only think holistically, but also be creative in accommodating change. System engineering can help to synchronize the needs with the available infrastructure and environment in order to balance the environment and meet predicted future needs, potentially by leveraging existing natural landscape and areas if available. Systems engineers must also contend with the resilience and adaptation of system degradations in response to natural and man-made disasters when developing a robust system. When designing future systems, the systems engineer should consider the wide range of users, services, and operating conditions. the future systems engineer can help to define these conditions and develop new and existing systems to provide these desired levels of capability. We also have environment and critical infrastructure. Multiple critical infrastructure sectors serve society, such as energy, water, communication, finance, government, and transportation. Addressing problems at a larger scale to accommodate larger and growing problems will be challenging to systems engineers to model, analyze, and test at a holistic enterprise and system of systems level. Incorporating the interdependencies between the various critical infrastructure sectors can also help to model the problem as well as apply systems thinking principles to discover the future required capabilities. Understanding how a system will interact with both society and the environment will also be challenging to the system engineer. Through systems thinking and complex adaptive systems analysis techniques, the system engineer can contribute to developing the enterprise-wide capabilities. We have cybersecurity and the Internet of Things, IoT. Increasing the number of connected devices within society can help improve the quality of life for all citizens. However, the improvement in security must keep pace with the threats in order not to ensure that the data are not corrupted with the original data intent it is preserved. System engineers must also consider trust as the important factor when designing systems to interoperate with humans, as well as ensure that the system making decisions are also considered systems safety and security. When developing the system engineers need to understand the divide between all humans, all machine, and a blend of human-machine decision-making, particularly as systems increase their edge computing capability. With a large number of interdependent systems connected together that require power and communication links, the system engineer will have challenges to define the challenging requirements, architecture, and design at larger scales and faster deployment times. We also have autonomous systems. As advances continue in intelligent autonomous systems, their acceptance and complexity will require comparable systems engineering development. Such systems include unmanned vehicles, robotics, aerospace systems, manufacturing, development, and assembly, human direct drug delivery, and financial trading systems. The methodological and thorough approaches of system engineering is required for autonomous systems to address the complexity, societal, and ethical issues that arise during their development and operation. Autonomous systems can go where people can't. They need to respond to unexpected, non-deterministic changes in the environment. System engineers will lead in concepts to realization of these world-changing systems. Finally, we have manufacturing. The future system engineer can apply their contributions to the manufacturing in order to keep up with increased and changing user demands. As users change their desires for more tailored products to customize their user experience, the manufacturing organizations and systems must be more agile to adapt to these changes at speed and scale to meet the demand. As a new product will need to interface with existing systems and be backward compatible, these systems will now need to accommodate additional complexity, interfaces, and data exchange. The use of interdisciplinary methods to consider the technical, societal, and user needs when developing a system will be a challenge to the system engineering team, particularly during the conceptual design, integration, testing, and deployment phases. Well, let's also consider the education for the future systems engineer. To stay ahead of the demand for improved system engineering products and services will require the system engineering education to be reevaluated to improve value to the existing system engineering education. Time-tested concepts, processes, and approaches discussed in this book and the lectures that we've gone over are the foundation all systems engineers should follow. Listed below are several topics to explore to continue to produce quality system engineering products. First of all, we have the core system engineering topic. System engineers must maintain their competency in the core capabilities of problem definition, requirements development, architecture construction, trade study analyses, and test and evaluation. Maintaining proficiency in systems engineering tool sets can help to interface with other customers and industry partners in order to contribute to system engineering product development and thinking. Tool sets are emphasized in order to expand the influences and compatibility of the engineer's thinking, but does not replace the thinking of the systems engineer. Additional proficiency in advanced topics such as systems of systems and complex adaptive systems analysis can help with looking beyond a single systems mentality. We also have system thinking and a holistic perspective. Future system engineering can help develop a comprehensive approach towards systems development through greater use of system thinking and a holistic perspective in order to look at interdependencies of the system, consider different perspectives such as users, other systems, policies, cultures, or environments can provide the system engineer with a better understanding of the significant drivers of the system performance. This can lead to a series of richer requirements and can help the system become more resilient when faced with system degraded performance in situations such as disasters or obsolescence. There's also transdisciplinary development and diverse teamwork. System engineers should be able to operate seamlessly within diverse teams in order to account for different users, perspectives, and needs. The teamwork can also build a robust set of requirements and assist in building comprehensive system architectures to fully describe the needs, functionality, and interfaces. Incorporating different disciplines from a design perspective can provide additional insights into requirements and interfaces during the development. Teamwork is especially critical with software-intensive products and service systems. The system engineer must effectively incorporate software engineers and developers in the system engineering process, especially with the majority of future systems having software elements. We also have model-based systems engineering and digital engineering, so also called MBSE. Developing systems with an MBSE environment can assist the system engineering team and the stakeholders by providing a means to quickly visualize the product in modeling ecosystems rather than a document-based static approach. This dynamic interaction of ideas and products can also help to shorten the system engineering lifecycle duration, eliminate errors during the out-of-sync documents, and permit rapid impact analysis to support decision-making. Being able to compare system alternatives and evaluate testing and maintenance procedures with a digital twin can help to anticipate issues before they emerge and help to prolong system operation. We also have Internet of Things and complex adaptive systems analysis. System engineers should be conversant with connected systems, devices, organizations, and users on a larger scale in order to consider how all of these objects may be expected to operate. As all of these independent objects operate and interact in the environment, different behaviors that were not planned or predicted during development may emerge, leaving the systems engineer to assist in understanding and sharpening the new behaviors and rules needed for a system to successfully operate. By performing these complex systems of systems configurations can then be considered in order to develop informed analytical products to serve all systems operating in the ecosphere. We also have education beyond traditional modalities. systems engineers must also consider education beyond the traditional formats, such as face-to-face or online course modalities. Augmented reality and/or virtual reality technologies are two areas that may be considered to help expose the system engineering practitioners and students to see systems operating in their perspective of the different stakeholders, thus gaining more insight into developing holistic and more realistic requirements. Global cooperation and collaboration that spans traditional academic boundaries may also become a new norm rather than an exception. Finally, we have agile system engineering. Agile system engineering approaches may be considered as a new approach towards system development as opposed to traditional system building, particularly as the user base and mission space becomes more flexible and demands more changes. As more systems become developed using this approach, the system engineer can help to shape the development and organization of the effort and interoperability both within and external to the system boundaries. As a threat to the system may change their behaviors as well, and agile approaches may be needed to quickly identify the relevant and non-relevant parts of the system that may adapt to the new challenges. Well, let's just focus on a few concluding remarks, and then we'll do a summary review. First, it's an exciting time to be a systems engineer. I think this continues to be taking place. I've seen this in my whole career. To see the progression of a single systems development or system methodologies mature to handle the complex problems of the world should be inspiring system engineers around the world. And to help you find that, NASA is a good repository of a lot of information that you can see system engineering being applied. The James Webb Space Telescope is a recent example. With a growing recognition of systems engineering as an academic field of study as well as a profession, system engineering can assist in many facets in today's society, from developing new and innovative capabilities, discovering where old concept needs new ideas, and integrating these new systems with legacy systems and natural environments when deployed. So it's nice, and I encourage you to welcome change. In fact, system engineers can be the leaders of the future in the creation, development, and deployment of new systems. And I would just hope that you all would enjoy your career and to begin to think and maintain thinking as a systems engineer. Well, let's do a summary for this chapter, and this will be the end of the material that we have for this course and also for this lecture. First of all, introduction and motivation. System engineers may need to adjust their thinking and adapt to new problems sets injected into society as a result of the changes to the system or disruptive events. Changes can include changes in user needs, system mission changes, competition teaming changes, changing threats performances. Disruptions can include technology, processes, and people system interfaces. Areas where system engineering approach can be applied, the system engineering approach, the system engineer can apply the system engineering approach and adapt to new challenges to a variety of domains: healthcare, transportation, environment, cyber, and Internet of Things. Plus, we talked about autonomous systems. Plus, we have manufacturing. Next, we have education for the future systems engineer. Systems engineers may need to reconsider the traditional modalities of system engineering education. Some of these areas for consideration may include core system engineering topics, system thinking, transdisciplinary of ideas, model-based system engineering and digital engineering, Internet of Things, and complex adaptive systems, education beyond traditional modalities, and agile systems engineering. All right, well, thank you very much. That'll end it for this lecture.